All right, let's go ahead and start to get into section 6.4. So section 6.4 is a continuation of 6.2 in that it also deals with means or averages, but this time it's going to have two different groups. The formula for calculating standard error is given to us. And again, this here is a way that we can get SE as opposed to the way we were doing it in chapter 3, which was with the bootstrapping many samples. It does also, um, it does require, though, noting a few different things. First, because we've got two groups, there's going to be a sample size for each of the two groups. Maybe they're the same, maybe they're different. The sigma that you see here is the standard deviation for each group. Here, I'm going to circle that and circle this. But the two that you see on the outside or right above it is a power. So it's being squared. Again, how they came up with there is a derivation for this formula, meaning there's a way to like how did they create this thing. But in our class, we're going to just appreciate that someone is offering to us this formula so that we can calculate the standard error whenever we're dealing with the difference between two different groups. Now, what we'll need in order for this first page was just an exercise to use the formula. This is a study about salaries of baseball players, and you can see here that um, the main stuff we need is the standard deviation. And they said the average salary for pitchers was $3.189 million. And there it is, standard deviation of 4.288. Meanwhile, for the other group, which is the batters, you can see their salary, $3.683 million with standard deviation of 5.060. And then what we're doing is we're supposing if we were to bootstrap this, where we were doing samples of 30 pitchers and 50 batters. What I've underlined so far is everything that we need for standard error. So we would do SE is equal to the square root. And then we can start off with the first group, which is the pitchers. They had a 4.288 standard deviation. That's going to get squared. And then we're doing 30 pitchers. And then for the second group, which is the batters, they had a 5.060 squared standard deviation. And then we're going to do 50 batters. And this is what you would put into your calculator. Again, if it doesn't work the first time, it should come out to be 1.061 if we keep three decimal places. Again, if it doesn't come out the first time, you might need to experiment to see whether your calculator needs parentheses or maybe it doesn't. Here, I'll put one way for a real basic calculator. For some, you might need parentheses around the information. And even if it's like a straight line, it could look something like this. Again, I'm just doing it for even a calculator that I've got that sometimes I'm using just for class. It does need me to maybe put it in something like this. But again, if you get 1.061, that means you're putting it correctly into your calculator. That's all the first page is. It's just introducing for us. And yeah, if we were to use larger sample sizes, that standard error would decrease. But let's actually go ahead and use it within the context of a study. On this one here, we're going to be doing confidence interval for difference in means. So there's going to be two different groups, and we're going to see whether it's plausible that there is a difference between the groups or not a difference between the groups. The formulas here. The thing that's different about it is now right here they're using S1 and S2 rather than sigma. That's because what's going to be driving things here is our samples for group 1 and samples for group 2. So those are going to be S for standard deviation for group 1 and then S standard deviation for the second group. And again, they might have the same sample sizes, they might have different sample sizes. And then right here, both of these are suggesting that we're going to square the standard deviations. Now, in the last section, 6.2, we talked about degrees of freedom, being that you would take the sample size -1 whenever you go to the t-distribution. But now that we've got two different groups, the guidance here is whenever we go get t-star, and there's two sample sizes, use the smaller one and subtract 1 from it. Now, the reason why I left a little bit of white space here on the lecture handout is because there is a good chunk of little like information here and there, and we want to keep it all sorted. So when they were doing this study, Tribulus was a supplement that they were checking to see whether it would have a benefit on students. They have it here, the mean anaerobic lactic muscle power, or AAMP. And to test it out, they had 20 athletes use the supplement. And it says that it was 1305.6 was the mean with standard deviation. So yeah, there's several stuff. I'm going to underline these. Yeah, for the athlete group that used the supplement, there was 20 of them. That was their value, 1305.6. That was their standard deviation. And then maybe I'll put circles around the other group. The sample mean for the control group, that was 20 of those athletes who didn't use the supplement. That was their mean. And then their standard deviation was 6.8. And what we want to do is calculate a confidence interval for what's the difference between the two groups. But let's just take a moment to write down, like, here was the sample size for the Tribulus group. There was 20 athletes. And then over here, we'll do the sample size for the control group that didn't use the supplement. That was 12 of them. And then the standard deviation for the athlete group was 177.3, and the standard deviation for the control group was the 6.8. Now, all those numbers are going to come into play at some point, but right now for A, it's if we do the difference between the Tribulus group and the mean for the control group, and again, X bar, because these are the values from the samples or the statistics. And we do the Tribulus group first. 1305.6 was their mean, minus the mean for the control group. We're going to get a difference of 49.7. So this is something we've done before. Yeah, we've done calculating the difference between sample means. But the 49.7, that's the statistic. There was a difference whenever they compared the two groups. But now, again, the reason why we do hypothesis tests is to see whether that was a fluke or not. The reason why we do confidence intervals to see is whether zero is plausible or not. And so moving on with part B, it says the degree of freedom. Now, again, because you have two different groups, you've got size 20 and size 12, the guidance for the t-distribution is to do the smaller one. So the sample of 12 is smaller than 20, so our degree of freedom will be 11. Now, the reason why we're even concerned about the degree of freedom in this one is that we need to get T star. Now, remember, back in the day or earlier in the class, like, it used to be always, just 2 times standard error. Then when we got to chapter 5, it became 1.96 whenever we were doing a 95% interval, or it would be a 1.645 whenever we were doing a 90%. But now with the t-distribution, because it's very particular about what your sample size is, this is something very specific that we have to find for this sample size, and also considering that we want a 90% interval. So we're going to take both of these, and because it's confidence interval, we're not just interested in the left tail. We're not just interested in the right tail. When we get to part E, we're going to want the lower value and the upper values, the lower and the upper. So in other words, like we want a two tail, like what's over here, the lower, the upper value. And so let's go to the t distribution, and keep in mind 11 and 0.9 are the degrees of freedom, and also the size of interval that we want, the more narrow one. So let me get out of here. This is something I was working on earlier. Uh, Here, let me go to the home page. Again, remember, t distribution is right there next to the normal distribution. And immediately it's going to ask us for our degrees of freedom, which for this study, it's 11 because 12 minus 1. And again, we're not doing hypothesis tests right now. We're not doing like left tail, right tail. We're doing confidence interval, which will always be the two tail that you want to click on. Now, immediately it defaults to a 95%, but suppose we only want a 90. So we'll click on the 0.95 and 0.90, click OK. And then down there at the bottom, you can see the 1.796. And again, there's a minus because we're going to do a minus version. We're going to do a plus version. But 1.796 is the specific T star value that we would need for calculating a 90% interval of a sample size this big. Now, the standard error, the formula is up there. And again, remember what this includes is two different groups that are separated by an addition, but all of this needs to go under the square root, right? It's not square root of some stuff plus square root of some stuff. It's all big one giant radical. And the formula tells us that the standard deviation for the first group should get squared, and the standard deviation for the second group should get squared. And then they should each be divided by their respective sample sizes. So again, all I did there was just copy the formula, but putting in, this is the supplement group, and this right here is the control group. And when you put both of these in rounded, should come out to be, whenever you get your answer and you round it, you should get 44.086. And again, I usually like to keep 3 decimal places. 3 decimal places gives us a little bit more accuracy than 2 decimal places. And I think it's also kind of just a good habit to do that, to kind of just go with what the instructions say. So when you're checking your homework answer key, your answers match the answer key. But if someone were to round this to, like, let's say 44.1, or because they rounded to just 1 or 2 decimal places, it's going to throw your answers off from the answer key. But it's not wrong. It's just that you rounded a bit more than what I did. And usually that's not, a huge big deal. But again, 3 decimal places is better than 2. 2 is better than 1. But let's use this now. The reminder of how to calculate the confidence intervals here, and we have everybody. We have our statistic, which is the 49.7. We're going to do 49.7, but we're going to do a minus version and a plus version, where the T star is the 1.796. That's going to allow us to get the appropriate width that we're interested in. So 1.796, 1.796. And then our standard error is what we just got a few moments ago. And this is what you would put in your calculator to get your lower bound and your upper bound. And then also be sure, whenever you're doing this with your homework, that you do submit any of those evidences of you using Stackey as hey, you did your homework. You didn't just get the values from the key. You actually went and you're practicing and learning how to use the Stack key as a resource. But yeah, remember the the initial result was that the supplement was going to be better by 49.7. Like it would boost that that muscle power by almost 50 points. But now that we look at the interval, zero is plausible. Yeah, so uh, we would we would start with our typical, we're 90% confident, and I'm going to do that here just a second. I'm just plugging in my power cord. There we go. Yeah, we would start off with we are 90% confident that and then again, they already have the wording for us, that the difference in mean and aerobic, the AAMP between athletes versus tribalists and those with no supplement, we could use those words, that the difference, and then we'll say it's between negative 29.5 and 128.9. And then that's it for this one. Yeah, so mainly just introducing a new formula that helps us to get standard error as opposed to the bootstrapping, and the again, because these were smaller samples of just 20 athletes and 12 athletes. Remember what we talked about in 6.2, that anytime that you have a sample size that's smaller than 30, you should consider using the t distribution, because accuracy, you know you know starts to be questioned, but the t distribution compensates for those things. Now, based on the interval, is it plausible that the supplement has no effect? In other words, is zero difference plausible? And yes. Again, remember, I want you, when you are doing your interpretations, to let's all stick to the number zero, right? As our simple way of explaining why we're going to say that yes, no effect might be plausible because zero is contained in the interval. All right. So in other words, yeah, if they were to do the study again with a control group versus a supplement group, it could very likely switch, where all of a sudden the control group who didn't use the supplement, they had a higher boost in that muscle power, or they had a higher mean than the supplement group, which is not good for the producers of the supplement. They're hoping to find evidence that they are always going to be uh, adding more of an advantage to your muscle power. But this right here suggested that it might not. And then now let's do one that involves a hypothesis test. Now this one, you do need to keep an eye on whether it's left tail, right tail, two tail. We're going to be getting a p-value to see if we can reject a null hypothesis or not. So I want you to read this one. I want you to pause the video, read it, and a couple things I want you to do while it's being paused is I want you to do just like we did over here. Find these things for this new example. Like, what was the sample size for group one? What was the sample size for group two? What was each of their standard deviations? Here, I'm going to do a little bit of that, just kind of getting set up. What was the sample size for group one? What was the sample size for group two? What was the standard deviation for group one? What was the standard deviation for group two? And then right here, they want you to do exactly that, right? Find the means for each samples, subtract them. And again, of course, use your notation. Use right here. I won't give it away. There should be the notation where you're doing sample mean minus another sample mean. But pause the video and see if you can get through parts A and B. All right, so hopefully you gave that a shot. And here's what we found out. What's being tested is to see whether there's evidence that heavy drinkers have a lower mean heavy drinkers than light drinkers. So here I'm going to go ahead and just put all these down here. Whether heavy drinkers have a lower mean than light drinkers. And again, the null is going to say that heavy drinkers are going to have the same test scores as those as light drinkers. And again, I think our assumption here, we probably all agree that, yeah, if you are a heavy drinker and it comes to school, maybe you're not going to perform as well as those who are light drinkers, or maybe even those who don't drink at all. Now, for the statistic, they gave us the sample means. They're both mentioned there for the heavy drinkers minus the light drinkers. It was a negative 0.2338. And again, you'll see all that up there. It's right. Boo, 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 boo. This was the mean for each of the groups, but for the heavy was the negative 2338 minus, again, just following this here, once this is do heavy minus light. The light group was the 0.1302. Excuse me. And the reason why I gave that guidance is because I wanted us to stick with a result here that showed that the heavy drinkers were lower by 0.364. And that was intentional. Notice that these are left tail with a negative statistic. Again, that way we're focusing on everything to the left, everything to the left. So this would be left tail. And then for the sample sizes, whenever they talk to the heavy drinkers, it came back to say that 83 of them reported being heavy drinkers. And for the light drinkers, excuse me, that was your light. Yeah, I saw that right now. Yeah, this was light drinkers. Those 83 of them, and then their standard deviation was 0.75. And then for the heavy drinkers, yeah, those not as many of them who said they were heavy drinkers, which was 16. And then the standard deviation for the heavy drinkers was 0.65. This way, when we come down here to do the standard error, we've got all that information just already like pulled out from that, all those sentences. And we know that it's 0.75 squared over the sample size of 83. And then now for your heavy drinkers, they had a standard deviation of 0.65 squared over sample size 16. Again, try this. Right now is the time to be trying. Now and in your homework, so whenever you get to the test, you feel really comfortable with putting this into your calculator, and you should get 0.182 rounded to, if we're rounding to 3 decimal places. Now, for your statistic, it's up there. The reminder is there, right? That if you're doing statistic minus null over SE to get your t-test statistic. So our statistic is what's right there. It's the negative 0.364. And then minus the null value. Remember, null right now is sent up to 2 groups, have no difference, which would be null value is 0. And then our standard error is 0.182. Now, again, you should from this get -2. And again, for some, if you need to, it might be that your calculator needs parentheses around there, or it needs you to do the subtraction first. But -2 is what we should get for um, our t test statistic. And then now, and again, that's negative, which is good because we're doing a left tail test. You are, for the t distribution, going to need degree of freedom. And because there's two groups, and again, these are the two group sample size. You got an 83 and 16. Remember, you'll have to make a little note on your reference sheet. If there's ever two groups, you have to go with the smaller one, which would be the 16 minus 1, which is degree 15. And so now with these pieces of information, left tail, degree of freedom 15, -2 for the t-test statistic, you can get the p-value from the t-distribution. And let's go ahead and let's go there and try it. Now I've got the t-distribution here. I'm going to erase the plot. Again, we can either escape and come back into the t-distribution or just click on edit parameters. And we can adjust this to be 15, which remember, degree of freedom, yeah, there's probably deeper conversation that we can have about what a degree of freedom is. But for our class, I want you just to think of it as it's a way of notating what our sample size is. And again, the -1 involves whenever they're doing the calculations for like standard deviation, standard error. It's embedded in there as a way to um, just try to get more accurately what those values are. But anywho, the 15 is in there, and then we've got left tail, and then remember the default p-value is 0.025, and we need to at the bottom put in -2. Right, -2.131 is not going to give us the right p-value. So click on that and type in -2. And now that you've got -2 in there, you should see your p-value of 0.032. 0.032. And I also just want to mention right now, with this class, a lot of these videos that you're doing in the lectures is you independently kind of going through like the course. And at the same time, there's maybe temptation to want to take extra resources that are not part of our class, such as like T tables or Z tables. We're not using those. So do not use those. Do not try to use those. They'll only end up being like a red flag that you're using things that you're not allowed to. You've got to use the stat key for this course, which has been true the entire since whatever week we started using stat key. It's always been stat key as our required resource for this class. But 0.032 is our p-value, and we've got that right here. And then again, let me not spoil this for you. Go to take a few moments. With a p-value that is that size with an alpha of 5%, would we be able to reject HO, not reject HO? Is there enough evidence? Not enough evidence? And I'll be quiet for, I mean, pause me and maybe if you need to look at some of your more recent notes and go and write your formal generic conclusion and the conclusion for this. All right, but here it comes. Again, yeah, because this is smaller, a less than 5% chance that this was a fluke, we'll say that that result is significant in that it was most likely not highly due to just being a fluke, that it would probably happen again. So we can reject the null hypothesis and say that there is enough evidence. And you can also say, I've also sometimes seen students who like to put there is sufficient evidence, but you have to have something to start off whether there is or there is not enough evidence to suggest or to support the alternative, which in this one was that the heavy drinkers are going to have a lower But in short, what we're doing here is we're trying to make sure we refer back to the context or what the whole purpose of the study was investigating. They're going to have a lower mean cognitive. Let's kind of go back up there. Heavy drinkers have a lower mean cognitive score than light drinkers. All right, but that is the conclusion of this lecture. Again, nice, um, easy peasy, straightforward one. It doesn't introduce a new formula for us. Now, do not be concerned about memorizing the formulas. These that we've seen since 6.1, 6.3, 6.2, 6.4, they will be provided on the test. I mean, you're welcome to put them on your reference sheet, but you'll also, when you are going through the homework using these formulas, at the same time see on the quizzes that sometimes the quizzes, uh, you don't need some of the formulas because they already give you either the standard error. And so it's like one less thing you might have to do on the test. But still, the heart and soul of these test three, test four that were uh, either that are happening now or about to happen are all hypothesis tests. So, and confidence intervals. Okay. All right. Well, I'm going to go ahead and end the recording there. Have a good one.